extreme value distributions, we're going to explore the probabilistic behavior of minimum and maximum values in a series of data samples. Okay, so we'll talk about what that actually looks like. We will define 3 classes of extreme value distributions, which describe PDFs and CDFs of minima and maximum values. And so you can imagine, well, the example we'll talk about is a sample of 365 days of the average daily flow on a stream gauge. So you have 365 as your sample, and then in a given year, you'll have a minimum or a maximum discharge rate. So you've got a distribution of daily flows, but you also have a distribution of the minimum and maximum values for each year. So each year is a sample, and then say over 30 years, you have 30 minimum, 30 maximum. So we're just talking about the distributions of those one value, minimum and maximum values of a sample. And then we'll apply these distributions to calculate the probability of extremes. Okay, so we're talking about extreme stats. We're not in the world of averages anymore, although you can take the average of an extreme value, average maximum, for example, or the variability or the variance of the maximum. So we're in the extreme world. Why do we care about extremes? I'll take your guys' thoughts. What are some examples of extremes that we care about in engineering or just in life?
Droughts, probably.
Say again?
Droughts, like extreme droughts.
Yeah, droughts, extreme droughts. So the minimum snowfall value that we get in a given year, right? Extreme pandemics. How often do we get pandemics that shut the whole world down? Natural hazards, obviously, we're talking a lot about natural hazards. So floods, droughts, fires, hurricanes, earthquakes. These all are things that occur. You know, every year there's a flood. The river floods or has a maximum discharge value. But we're really interested in the extremes of the extremes in those cases. So in engineering, there's a lot of examples. Some of these extreme distributions came out of looking at material strengths. So say we're testing some steel beams or concrete samples or something like that, and we're looking at them under the microscope, and there's going to be a distribution of crack lengths after we apply some stresses to it, or minimum or maximum breaking strengths in a sample of these steel bars. So material properties are important. Electrical systems, you could imagine that, you know, in a given day, there's a minimum and maximum load on an electrical grid. And then, of course, we have like the annual minimum and maximum values. You could imagine, I'm also thinking of, okay, we're talking about electricity. Well, you guys in hydraulics are designing water distribution systems, and you're interested in the minimum and maximum demands on the water distribution system, in which case extreme values would be important. Finally, economics, markets crashing. What's the biggest daily drop over a given year? Insurance companies are really interested in, you know, natural hazards as well as just the risk of their insurance portfolio. So economics, there's a lot of extreme values distributions that people care about. Okay. So one of the questions as engineers that we have to encounter is, do we design infrastructure to withstand extreme events? Are we, obviously to a certain extent, right? But not everything, and maybe not the most extreme event. In hydrology, we'll spend some more time talking about kind of what events do we want to design for, or what probability. Do we avoid extremes? Do we want to design systems that are really robust and can withstand that tsunami wave or that huge flood or that hurricane wind load, or do we try to mitigate or avoid those natural hazards? Either way, we still need to know what they are. We need to be able to map them, estimate them, characterize them, and that's why we deal with extreme stats and extreme distributions. Okay, so for our example, we'll talk about floods and just kind of introduce you to this concept of extremes. So previously you guys dealt with data from the USGS stream gauge website. We downloaded data for Fish Creek and Steamboat, which was a smaller creek, and then the Colorado River down here in the Grand Junction area. And what we downloaded was average daily stream flow data. And so, you know, I think maybe we had a 10 or 30 year or even longer record. And so that data series then is 365 times, say, 30 years or something like that. So we have a really big data set that describes the distribution of average daily flow. All right, and so that's what that might look like if X right here is our, if X is our random variate, and this is the distribution of X right here. So maybe it's a log normal distribution or something close to that. And it's going to have an average daily flow rates with a mean of the logs and standard deviation of the logs. And so this is the distribution of X. And so with this distribution, we can ask questions like, what's the mean daily flow rate? What's the 99th percentile? What's the standard deviation of the flow? So we can ask all these things. And this is all about daily flow, right? So mean daily flow. But say we're actually interested in floods or droughts, right? So we could do the maximum or minimum values. Floods usually occur over a day or a week or something like that on rivers. However, bigger rivers, obviously the floods can last longer. I think the Mississippi River floods can last weeks and weeks. But droughts are typically things that kind of like creep up. And so for droughts, you might be interested in something like the total snowfall up until March or something like that in the mountains. So a mean daily flow or a mean discharge record or rainfall record wouldn't really tell you much about droughts. So, but for floods, okay, let's look at the maximum annual flow rate. Okay, so our sample then is going to be 365 days on a river. And we'll let y equal the maximum daily flow rate over n equals 365 days. So now, instead of x was our random variate right here, for the daily flow rate, y is going to be our random variate. And this is the maximum value out of 365 days, maximum daily flow rate. I should say this is y sub n, which refers to the largest value. So y is going to follow an extreme value distribution. X follows a log normal distribution. Y is going to follow something that's like, it's not like a log normal, I shouldn't say, but it's related to the log normal. And because we're in the same chapter as the derived distributions, it's a function of distribution. So it's a function of the log normal distribution. Okay, so extreme value distributions describe the distribution of minimum or maximum values of a sample. And so each sample has a minimum maximum value. The sample has n values within it. And then we have so many samples and so many minimum or maximum values. All right, so if we had a stream gauge of 30 years, we'd have a really large, we have 365 times 30 values of X, but we'd only have 30 values of Y sub n, right? So 30 annual maximum values. And this is what that distribution might look like. Okay, and so our distribution of X right here, this is the log normal distribution. Our distribution of Y sub n, this is the maximum. This is our extreme value distribution. And what it shows is we're looking at the tails. We're looking at the behavior of the extreme values which fall along the tails of this distribution of X. And the tail is that long kind of thin line that comes out here. Very low probability, but really big values, right? So this is the territory of the annual maximum minimum. So that PDF overlays it, and it's its own PDF, right? And it overlays the region of Q where we have those maximum values. So it's a different distribution, but it's related. So f of y is the extreme value distribution PDF, and it describes the behavior of the tails of x, all those maximum values. So we're going to do just kind of a generic derivation of extreme value distributions. So x, again, follows that log normal distribution with mean of the logs and standard deviation of the logs. And I probably should just scribble these out because that y is going to confuse you. But usually when we say log normal distribution, we're talking about the mean and standard deviation of the logs. But I don't want to confuse that with the actual minimum and maximum values. So now let's say we take a sample of x. So x1 is the first sample of n values. x2 is the second sample of n values, all the way up to n samples. So if we had 30 years of a stream flow record, we'd have x sub 30. And so this is so many samples of x. And so these are all those samples. And then we'll say yn is going to be equal to the max of all these samples. And all these samples came from this distribution of x. Okay, so this would be our annual maximum series. So y sub n is the maximum of all those samples. Y sub 1 is the minimum of all those samples. 1 means the first value if you rank them. N means the last value. Okay, so let's choose some arbitrary value, small y. And we'll say that yn is going to be less than y. So this is just some upper threshold. Okay, so then all the samples of x will individually be less than y. And so if we assume that these samples are statistically independent, and then all the underlying CDFs of each of these samples, so x1 has a CDF and a PDF, x2 has a CDF and PDF, and so forth. These should all be equal because they came from the same x value, right? So there's, if you take a sample from a value, it's going to have the same distribution as the actual value. It's because it's at least underlying distribution. So that means that the overall CDF of x is going to be equal to the CDF of x1, of x2, all the way to xn. So all these CDFs are going to be equal to each other. And then our CDF of the maximum value of all these series, so f sub yn of y, so the CDN of the extreme values would be equal to p, probably that the x1 is less than or equal to y, so all the values in that sample are less than, and x2, and all the way to xn. So the way to write that out now, using our probability theory and the fact that this is statistically independent, is we can just say, okay, well, because these are all equal to each other from here, then we can just say it's the CDF of x to the n. And n is the number of years on record, for example. So all we did is we just said, okay, we'll take the CDF of x and we'll multiply it by itself n times, where n is the number of samples that we took. Okay, and now if we have that CDF, the PDF is just the derivation of that CDF, the derivative of it. And so we just do n, the CDF of x, n minus 1. And then when you take the derivative of what's inside, that, of course, is the PDF of x. So what this says is that the PDF of y sub n is equal to n times the CDF of x to n minus 1 times the PDF of x. So it's a function of that original CDF and PDF. So we'll go through an example of this with the exponential distribution. And I'll stop for any questions if you guys have them. Is the text big enough for you to see? Okay.
I have a quick question.
Yeah, please.
So how come for the PDF? So if you go back to the equation you gave us for the PDF, how come the PDF is like in there when we were trying to find the PDF? Or
So I say that again.
no, never mind.
The audio got a little scrambled.
Oh no, I see now. I'm
Okay.
good.
The CDF's pretty straightforward, right? Because we're just saying, okay, for each sample that we had, we're just multiplying the CDF by itself and raising it to the power n. The PDF is really just the derivative, and so you're taking that function, you're just put that exponent down, take 1 minus the exponent. We've got that function inside, and then we take the derivative of the function, which ends up being the PDF. Okay, so what this means is that the CDF and PDF of yn are a function of the original distributions of x, that original variate. So if yn is our maximum daily discharge over 365 days, and x is our daily discharge, yn ends up being a function of those log normal distributions. And then I'll just give you the CDF and PDF of the minimum value, so y sub 1. So the CDF of y sub 1 is going to be 1 minus f x of y. So this is just the CDF of x raised to the power n. And then the PDF is the same format. Now we're just taking the derivative of this inside. So n, 1 minus f of x, and then big F of x and then little f of x. So this is for the minimum. So you're going to have a different distribution for the minimum values and a different distribution for the maximum values. Okay, so let's do an example. So x is going to be the standard variate, and x is going to be an exponential distribution. It's the time that it takes to get through an intersection during rush hour. So we're sitting in rush hour. Rush hour doesn't exist in the world anymore. So I don't know why I thought of that, but here we are talking about it, because someday rush hour will come back. So you're sitting at a light, and this is the average time it takes to get through this intersection for any car. So on average, it takes 2 minutes to get through the intersection during rush hour. Because this is a waiting time, waiting times typically follow exponential distributions. So we'll say x follows an exponential distribution. And then our lambda. Our lambda, which is the rate, is going to be, in this case, we're doing with minutes. So you cross the intersection 0.5 times per minute, right? So on average, it's 2 minutes. So 1 over the time it takes to get through intersection is our rate parameter for this exponential distribution. So this is what our exponential distribution looks like. So we have our wait time on the x-axis. We have our PDF of x. Here's the CDF of x, and here's the PDF of x. And you'll notice that, if this is our PDF, if you take the derivative of this, this is what you get. So that makes sense. These two are related because one's the derivative of the other. So we have a lot of really short wait times. We have that average of 2 minutes is our average wait time, and then we have very few long wait times. That's our exponential distribution. Okay, so one of our parameters is the traffic jam occurs if the wait time is greater than or equal to 10 minutes. That means traffic backs up all the way to the next block, and so we get a traffic jam, and cars are starting to get clogged up everywhere. So what's the probability that our wait time is greater than 10 minutes and then we get a traffic jam? Well, we go to our exponential CDF, because whenever we have an inequality, this means we want to evaluate the CDF because that's a cumulative probability. So this would be all the probabilities at 10 minutes and greater than. So that's why we do 1 minus f of x, because big F of x, or the CDF, when we plug in a value, gives us the cumulative probability up to, so less than or equal to. So we'll take the complement of that. And we just plug in our numbers. So lambda is equal to 0.5, x is equal to 10 minutes. And we get the probability of a wait time greater than 10 minutes is about 0.7% or 1%. So pretty low probability that we'll have that wait time. Okay, so now let's look at a different question. What's the distribution of the maximum wait times over a 2-hour rush hour? So rush hour takes 2 hours to happen. What's the distribution of the maximum wait times that we experience on a given day? So each day we have 2 hours. We have all these wait times. We want to know the maximum wait time on a given day across all the days. So if we have, or say we have 2 rush hours in a given day, then we have 300, or we'll do 5 days a week times 2 rush hour periods times 52 weeks, and then that's how many maximum wait time values we could get from this data set. Obviously, much less than the individual wait times that every car that would pass through the intersection would have. And that's what this would. This is like the individual cars, and here is the car that took the longest to get through the intersection. So we'll define our yn as the maximum wait time over n equals 120 minutes, because lambda is in units of minutes. That's what our n value is going to be. It's 2-hour periods. So we have all these samples, right? And then we will derive our CDF. So remember, our CDF is simply just the CDF of yn, the maximum values, is the CDF of x raised to the n. So if this is our exponential CDF, 1 minus e to the negative lambda y, we just raise that to the power n. And so this is going to be our extreme value distribution, CDF, with the lambda value in there, with the n value in there. And then here's our PDF. I apologize for that over here, but we'll show it. The generic example is n times the CDF raised to the n minus 1 times the PDF of x. And so in this case, this is what our extreme value PDF will look like. And then this is what it looks like when you plug those numbers in. Just so that's going to be times e to the negative 0.5 y. All right, so now we have our extreme value distributions. It wasn't too hard, I chose the exponential distribution because it's just easy to, get the derivatives of it. So now that we have those distributions, we can ask, what's the probability that the maximum wait time is greater than or equal to 10 minutes over a 2-hour period. And obviously this distribution is going to be different depending on our n. So 2-hour period means n is equal to 120 minutes. So we would get an actually different PDF and CDF for this extreme value distribution to be a totally different function if rush hour was a 3-hour period or a 1-hour period or something like that. So that the n, or the number of samples that you're interested in, influences the extreme value distribution. So to formulate this question, then the probability that y sub n instead of x, now we have y sub n greater than or equal to 10. And this is going to be equal to 1 minus the CDF of y sub n evaluated at 10, because we're doing greater than or equal to. I should just draw that little CDF for you. So if this is our CDF, and this is 1, this would be our maximum wait time. Then say this is 10 minutes as the maximum wait time. We want this upper value, right? So our CDF, when we plug it in, gives us this value, which is the cumulative probability, but we want this upper value, which would be 1 minus. So we'll just plug in our values. Lambda again is equal to 0.5 crossings per minute. N is equal to 120 minutes. That's our sample size. And then our Y value is 10 minutes is the wait time that we're interested in. So plug those values in. And we end up with a much greater value. So the probability that the maximum wait time over 2 hours is about 56%. And that's much greater than the probability that the average wait time, or the probability that the wait time just in general would be greater than 10 minutes. So over 2 hours, we have a pretty good likelihood, a half a chance over 2 hours of having a wait time greater than 10 minutes, which means we have about a 50% chance of having a traffic jam. Okay, so maybe there's a problem with this intersection, right? And so let's just look at what those two distributions would look like. What's the difference here? Christian, I'll ask you, why is this 50% greater? If you could just rephrase that for me, greater than that 0.7% that we calculated, the two different wait times. Let me unmute you. There you go.
For the y of n, it means that it's more towards the center of the distribution, while for the f of x, it's towards the tail of the distribution, so it's a less common but higher number.
Great, that's a great way of putting it. So if this is 10 minutes, yeah, exactly. So you have about, 50% of the area is under that distribution. I should write it over here, 50% of the area. But then when we look at the x sub n, we only have a really teeny tiny, right? This was 0.007. This was 0.56. So yeah, the two distributions are just different. And we're more likely to get a maximum value that's greater than 10 minutes than we are just to get a general value that's greater than 10 minutes. Okay, so we're reaching our kind of 40-minute saturation points. This is my last point for today, and there's 3 different types of extreme value distributions: type 1, 2, and 3. The tails for type 1 decay exponentially, and so of course exponential distributions, if x follows an exponential distribution or a normal distribution, then it's going to be a type 1. And type 1 distributions have a certain format. Type 2 distributions the tails of x decay as power laws or polynomials. And this includes log normal distributions. So if you have a log normal distribution, then the tail behavior will follow a type 2. And then type 3 have finite bounds. And so that means there's an actual, you know, we know that the minimum value is 0 and the maximum value is 100 or something like that. That's a type 3, and it's called a Gumbel distribution. And there's actually what's called the, I'll just write it down. Generalized extreme value distribution. Or GEV. And this actually incorporates all three of these. And so it's a function that's flexible enough to, it's just one equation or one PDF and one CDF that accounts for all of these. And so I think for the lab, I'll have you guys, oh, actually no, for the lab's already posted, so never mind. But I think in hydrology, we'll have you guys work on that. So that's extreme values. I'll take any questions, and then we can also go over homework questions too if you have them. Let me just show you in the book too. I walk you through this in the lab for this problem, for this section. But each of these distributions has their own, let's see here. So here's the Gumbel distribution type 1. And it's got its own kind of generic format, and then they go through how to calculate the alpha and u values for those. So whatever, you know, if it's a normal distribution or an exponential distribution originally, the extreme value distribution, you can calculate these u values and alpha values based on the mean standard deviation of the data. There's also another way to do it that's based just on n alone, and I give you that equation for calculating u sub n and alpha sub n in the lab. So we'll go over that a little more explicitly, but I didn't want to take the time to go over that in class.